Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be teaching full bridge inverter. And here, this full bridge inverter consists of 4 transistors, namely T1, T2, T3, T4, as well as it consists of 4 diodes, that is D1, D2, and D3, D4. So, this is a full bridge inverter with resistive load, and here initially at a time any 2 transistors will be conducting. Initially T1, T2 will be conductor, and later T3 and T4 will be coming into the picture. So here we'll be providing the base drive for IB1 and IB2 at a time. Later we'll provide the triggering pulse, that is base drive for IB3, that is transistor 3 and transistor 4. These are the base drives which are being provided, and if you see for the transistor 1 and 2, we'll provide the base drive at a time, that is from 0 to T by 2. Again from this instant called 0 to T by 2, again from T by 2 to T, the transistor 1 is off, we are not providing any sort of base drive, and again at this instant called T, we have provided the base drive for the transistor 1 and 2. And for transistor 3 and 4, we are providing the base drive right from this instant T by 2 to T. And here output voltage waveform, when transistor 1 and 2 is conducting, at that instant, see here transistor 1 we have provided the base drive, so what transistor 1 is on and it is conducting current to the load, and again from T2 and back to phase. And if you see current is flowing from A to B, that means positive half cycle of the output voltage waveform will be controlled. That is, as long as we are providing the base drive, there is a output voltage through the load from 0 to T by 2. And with magnitude Vs is applied. With magnitude Vs is applied. And the moment we have withdrawn the base drive, transistor 1 is turned off. And now we are providing the triggering pulse or base drive for the transistor 2. Such that now transistor 3 and 4 are conducting. We are providing the base drive for the transistor 3 and 4, and thereby it is conducting current to the load from point B to A. That is reverse to that of the first case. So that is the reason from T by 2 to instant T, we are getting the output voltage negative. This is positive output voltage and this is negative output voltage, and we are able to get the waveform right from instant T by 2 to T. And again we are getting the output voltage controlled in the positive half cycle the moment when we provide the base drive for the transistor 1 and 2 again. And it will be conducting current from A to B. Transistor 1 and 2 will be conducting current through the load from A to B. So that is how positive half cycle of the output voltage is actually controlled. And this is the output voltage waveform due to T1, T2, and this is due to T3, T4, and again T1, T2, and the cycle repeats. And this is of magnitude Vs and in the negative direction with minus Vs. So this is the amplitude. And now talking about the output current, and if you see output current will be just similar to that of the output voltage, only because here we are making use of resistive load. So that is the only reason here output current where I0 is equal to V0 by R, and only a magnitude will be differing because we are inserting the value of the resistor, and because of which the magnitude will be a little reduced, or otherwise wave shape is one and the same because this is resistive load. So what we are getting the output current right from this instant the moment when we provided the base drive for the transistor 1 and 2. Transistor 1 and 2 is conducting current right from 0 to instant called T by 2, and this is the waveform due to T1 and T2. and the moment it reaches T by 2 instant, we have withdrawn the base drive for the transistor 1 and 2 and we provided for transistor 3 and 4. So what? Transistor 3 and 4 conducted, and this is the output current waveform due to T3 and T4. T3 and T4 is conducting current from B to A, reverse to that of the first case. That is how here negative half cycle of the output voltage is controlled, output current is controlled. So what we are getting? Output current right from this instant T by 2 to T. And again at this instant called T, we have provided the base drive for the transistor 1 and 2. This is the output current waveform coming to the current through the transistor 1 and 2. These two will be conducting at a time. So this is the current through the transistor 1 and 2. And if you see again at this instant, transistor 1 and 2 came into the picture, whereas here T3 and T4 was conducting. And this is the individual waveform across transistor 1 and transistor 2. Coming to the current waveform through T3 and T4. It is conducting when transistor 1 and 2 are off. This is right from this instant T by 2 to T. We are getting the output current through the transistor 3 and 4. And this will be of magnitude Vs by R. Hope you understood. Coming to the full bridge inverter with RL load. Here, base drive for the transistor 1 and 2. And this is base drive for the transistor 3 and 4. And here it is conducting right from this instant 0 to T by 2 and again from T to the other instant. And coming to the 3 and 4, it is conducting from T by 2 to T. So here when the base drive is provided for the transistor 1 and 2, from this instant 0 to T by 2, transistor 1 and 2 is conducting current through the load in this direction. That is from point A to B. So what? We are getting the output voltage from 0 to T by 2 with magnitude Vs. And again from this instant T by 2 to T, we have provided the base drive for the transistor 3 and 4. So what here? 3 and 4 is conducting current through the load in the reverse direction to that of the first case, that is from B to A. So that is how from T by 2 to instant T, we are getting the negative half cycle of the output voltage control. And this is due to T1, T2, and this is the waveform due to T3 and T4. And the moment it reaches T, again we have provided the base drive for the transistor 1 and 2. And so what? We are getting the output voltage with magnitude Vs, and this is minus Vs, and this is nothing but the output voltage waveform. Talking about the output current waveform, if you see when transistor 1 was conducting, see transistor 1 and 2 is conducting because of the presence of the inductor. Since we are talking about the output current waveform, because of the presence of the inductor, current will be building at a slow rate. So it is becoming maximum at this instant called T by 2. And the moment it reaches T by 2, there is already base drive waiting in order to trigger transistor 2. But still, whatever the energy stored in the inductor during when T1, T2 was conducting, and this particular inductor, it tends to maintain current in the same direction as that of the first case. See, let us observe. Initially, T1, T2 has conducted, and during which there was certain energy stored in the inductor, and by the time it is completely charged, the polarities are now positive, negative, and because of these polarities, now it tries to maintain D3 and D4 in the conduction state. Here T1, T2 is turned off, and because of the polarities of the inductor, and since inductor tries to maintain the current flow in the same direction to that of the first case, So what? Here D3 and D4 is conducting current through the load in the same direction as that of the first case, that is from A to B current flow. So that is the reason, since energy is providing energy, since inductor is providing the energy, inductor is dissipating current through the load. So whatever the energy stored in the inductor is slowly coming down and finally it is becoming zero. And the moment when the energy stored in the inductor is completely dissipated, it has become zero. And since there is already a base drive waiting for the T3 and T4, and this triggers T3 and T4. So what? Now T3 and T4 came into the conduction state, and now current through load is flowing in the reverse direction to that of the first case, that is from B to A. So that is how we are getting the current building in a negative direction at a slow rate because of the presence of the inductor, and by the time it reaches T, we have withdrawn the base drive for the transistor 2. So our transistor 2 is turned off, but now inductor tries to maintain the current flow in the same direction from B to A. So that is the only reason what it does is it forward biases D1 and D2. It forward biases D1 and now D2. So that it can maintain the current flow in the same direction, that is from B to A. So what? Now whatever the energy stored in the inductor is getting dissipated. Because inductor is giving the energy, the current through the load will be becoming reduced, and finally it becomes zero at this instant. And at this instant again T1, T2 we provide the triggering pulse. So what the cycle repeats, and here at this instant D1 and D2 conducts, and at this instant D1 and D2 conducts. So this is all about the output current waveform due to the presence of the inductor. And now current through the transistor 1, exclusively current through the transistor 1. As long as transistor 1 is conducting, we will get the waveform through the transistor 1. So if you see here, D1 and D2 was conducting till this instant to this instant. Now here at this instant T1 came into picture and it is conducting, and now base drive for the transistor 1, since it is withdrawn, now current through the transistor 1 is 0. And again at this instant when T1, T2 is conducting, we will get the output current waveform across the transistor 1. And this is the current waveform for ID1. When diode 1 is conducting, we'll get the waveform. Again, when diode 1 is conducting, we'll get the waveform. Talking about the supply current. See, as I told you, when all the devices are conducting, there is a path through the supply. See, if you see, when T1, T2 is conducting, there is a path through supply. When T3, T4 is conducting, current through the load, there is a path through supply. And when D2, D1 is conducting, there is a path through supply. And when D4 and D3 is conducting, there is a current path through this particular supply. So in all the cases, when any device is on, at that instant, there is certain amount of current which is drawn from the supply. So what? We need to indicate the supply current every time. So here supply current is indicated, again supply current is indicated. And this is the supply current waveform. And if you observe the limits, magnitude is Vs, and it is conducting from 0 to T by 2, and negative half cycle is again conducted from T by 2 to T. Let us examine the V0 RMS expression for single phase full bridge inverter. The general formula is 1 by T, 0 to T, V0 square of omega T, d omega T, whole to the power of 1 by 2. And here with magnitude Vs square of omega T, d omega T, whole to the power of 1 by 2. And let us substitute the limits here. 1 by T, it is conducting from 0 to T by 2 with magnitude Vs square, plus again it is conducting, negative half cycle is conducting from T by 2 to T with magnitude minus Vs whole square d omega T whole to the power of 1 by 2. So that is the reason here constant Vs square, bringing it out Vs square by T. And if you see, the limits are T by 2 minus 0, T by 2 minus 0 plus T by T minus T by 2. If we simplify, we get V naught RMS is equal to Vs square by T, and this is T by 2 plus T by 2. T by 2 plus T by 2 is T. T gets cancelled, and this is whole to the power of 1 by 2. So that is the reason here V naught RMS is equal to Vs. So single phase, a single bridge, full bridge inverter with R and RL load, V naught RMS expression is Vs. And in the coming up lecture, we'll be discussing PWM techniques. Thank you.